Okay, welcome to the second session of the discussion on the topic of rheology. So today we are going to discuss on the topic of rheology, and that's the about the liquids we classify under the Newtonian flow. Now, I think you got it. This is a glass of water, and I just drank it off. So why I'm why I drank this water is to show you that today's topic is somewhat related to that liquid. So let us go to the topic. So understanding the Newtonian flow, it has two words or two things which you have to understand. Newtonian flow is generally considered to be produced by those liquids which is having a proportionality between the shear stress and rate of shear. That means as the shear stress increases, the rate of shear also increases. So I will explain it one by one. So today's topic is Newtonian flow, hopefully. So in this Newtonian flow, I'm going to explain it with this syringe. Okay, so you can see this syringe. So this contains the same liquid which I had over here, water. So what I'm going to show you that when I'm applying, so you can see it over here, when I'm applying very less force, if the liquid is moving very slowly, as okay. So when I start to increase the force, you can see the flow of the liquid also increases. You can see over here. And now I increase the force to its maximum. You can see it's flowing as a fine straight flow line. You can see it over here. And I'm still increasing and still increasing. And that movement or the flow rate is also increased. Okay, so the force which I was applying to the piston, okay, the force which I was applying to the piston, this is what we call it as the shear stress, force applied per unit area, that is the shear stress, and the force is over here. And as you can see, as I start to increase the force, the rate of the movement of the liquid per unit time also increases, the speed increases. So that's what we call it as the rate of shear. So there are two things. One is shear stress. Shear stress is nothing, that is force applied per unit area. You can see it over here, force applied per unit area. And you have seen the movement of the liquid which was coming. As I was increasing the force, the movement or the speed was also increasing. That is the means the what you can call how quick or fast the liquid moves, or you can say the deformation per unit time. That's what we call it as the rate of shear. The rate of shear is denoted by the sign called G, and the shear stress is denoted by the sign called F. Now you can see what Newtonian flow suggests is the force per unit area, that is rate shear stress, is directly proportional to the rate of shear. That is, as we increase the shear stress, the rate of shear also increases. As we decrease the shear stress, the rate of shear also decreases. So that's the concept. Okay, so they are directly proportional. If you can see the graphical representation over here, you can see the graph over here. The graph suggests that the shear stress and rate of shear are linearly correlated to each other. This linear correlation generally occurs when they are directly proportional to each other. Please remember this thing. They are directly proportional to each other. Now, one thing after this, so if we want to equate this proportion, or if you want to remove this proportionality sign, so we need a proportionality constant. So here the proportionality constant is nothing but viscosity, which is represented by the sign eta. So that you can see that sign F equals to proportionality constant G, or the proportionality constant, which is nothing but the viscosity, equals to F by G. You can see it over here. It is denoted by the sign, by this formula. That is, shear stress divided by rate of shear is what is your viscosity. Is what is your viscosity. The thing we should remember is that this viscosity, this viscosity is the intrinsic property. That is, it doesn't changes with the quantity of the substance present with you. It will be a constant based on the material what you are using. Okay. So the unit which we are having for the viscosity is called as poise, centipoise, or SI unit is called as the poise. So we should remember, like um, um, measurement. So previously when I was discussing my initial topics, I told that everything has to be divided into or segregated into multiple sections. Here we should know how do we measure this viscosity of the Newtonian fluids practically. The most common technique which is being used over here, we call it as the capillary method, known as Oswald's viscometer. So Oswald's viscometer is the viscometer built for the Newtonian liquids. I repeat, to measure the viscosity of the Newtonian liquids, mainly we do use the Oswald viscometer. You can see it over here, Oswald viscometer. So Oswald's viscometer, you can see there is a capillary and there is two marks over there. There are two marks over there, A and B. So we need to pull that liquid through the capillary to a mark which is at the top, and then leave, and from that upper mark, what you can see over here, the upper mark, we leave it. So let it flow downwards along the gravity from the upper A to B. So as it moves from A to B, we measure the time which is required and we compare it with a standard liquid. So that is how we measure in an Oswald viscometer. So it is a capillary viscometer. Please remember this point. It's a capillary viscometer and mainly it is used for measuring the Newtonian liquids. Okay. So what we came to know, just recap once more. In the case of Newtonian liquids, the shear stress is directly proportional to the rate of shear, and the constant over here is called as the viscosity. It's called as the viscosity. Now, what we come to know is there are examples. So when we go for the examples of the Newtonian liquids, they are of two classes we come to know. One we call it as viscous liquids, viscous Newtonian liquids, and non-viscous Newtonian liquids. So when we say of viscous, non-viscous Newtonian liquids, we have water. We have water. Along with water, we can have other examples like we can have ethanol, we can have chloroform, whatever. We can give the liquids examples as the non as non-viscous or low viscous Newtonian liquids. Whereas we go for viscous Newtonian liquids, we have something called as honey. We discussed honey. We have something called as what you call, as in the case of that, we have glycerin, oils. What will happen with them? So we show you this thing. So I have, this is my, so if I try to give the same force which the, you can see, the water was flowing, it's very hard to press it for the case of what do you call, for the case of glycerol, you can see. But still, if I increase the rate of stress, the rate of shear also increases, but in a much lower rate than that of the less viscous liquid like water. But it is increasing. As we're increasing the shear stress, the rate of shear is also increasing. You can see it has increased. But if I put much force, maybe this syringe will come out. But I'm trying. Let me see if I can. Yeah, it's very hard. But you can see it is increasing. Yes. So this is following a first order rate, very difficult with the case of glycerol. I have used the glycerol. It's a brand glycerol I have used over here. So just to show you the difference in the flow. So maybe in the case of water, the flow will be faster. In the case of this, it will be slower. But there will be correlation between shear stress and then rate of shear. Now, why it happening so? Why in this case it is slower and why in this case it is faster? Let us see the structure of water. So, when we see the structure of water, we have, there is a chance of only two hydrogen bonding that can be produced between the intermolecular force of attraction. Whereas we go for glycerol, there are multiple options for forming intermolecular force of attraction. So the intermolecular binding will be higher in the case of glycerol than in the case of water. So that's the reason the viscosity is higher in the case of glycerol or high viscous liquids than the low viscous liquids which are easily flowable. So that's the thing you should remember. Last topic regarding this is that even we say these things, isn't it? But there is an option where we can change the viscosity. There's a chance by which we can change the viscosity. Um, because as we know, viscosity is a constitutive property of a matter, intrinsic or constitutive property of the matter, which does not depend on the amount of that matter which is present with you. If you take it 1 ml, the viscosity will be what? If you take 100 ml, the viscosity remains the same. So that's the thing you should remember. The last topic of our discussion is the effect of temperature on viscosity. Effect of temperature on viscosity. So here, if we see the effect of temperature on viscosity, this is being explained by Arrhenius equation. This is being explained by Arrhenius equation. You can see the Arrhenius equation is written over here, where A equals to the Arrhenius constant, EV is the activation energy, R universal gas constant, and T is the temperature. So this is the exponential form of the equation. Now let us see if we represent it in a what you call much more linear type. So land form, it is being taken in the land form. So you can see one thing, the viscosity on the other side, you can see land of the viscosity on that side, and the temperature on this side. If you see, they are almost inversely proportional. Yes, they are inversely proportional. What it suggests? It suggests that if we if we increase the if we increase the temperature, the viscosity will decrease. Okay, if we increase the temperature, the viscosity will decrease. So generally what happens is, as we increase the temperature, there is a chance that your viscosity may decrease. So hopefully you understood these topics. So in the next part, we are going to start with the non-Newtonian liquids. If you like this channel and today's discussion, please put a like and subscribe the channel, and let me know any kind of queries in the comments below.